Hey folks, my name is Nathan Johnston. Welcome to lecture 36 of Introductory Linear Algebra. In the previous lecture video, we looked at one method for computing the determinant of a matrix. In this video, we're going to look at another completely different method of computing the determinant of a matrix. And then at the end of this video, we'll sort of compare and contrast them. We'll talk about when one method is advantageous over the other one. Okay, but for now, let's just dive in. What is this new method for computing the determinants of a matrix? Okay, well, the way it works is basically it's a whole series of explicit formulas for the determinants. Okay, so what we're going to do is we're going to come up with a formula for the determinant of a 2x2 matrix, then a 3x3 matrix, then a 4x4 matrix, and so on. Okay, so let's see how it works. To start off with a 2x2 matrix. Well, our first theorem says that if you have a 2x2 matrix, then its determinant is just given by this nice explicit formula here. Okay, it's just AD minus BC. Okay, so top left entry times bottom right entry, minus sort of the product of the backward diagonal entries. Okay, so first we're going to prove this, and then we'll go through a couple quick examples to make sure that we understand it. All right, so the way we're going to prove it is we're going to make use of the defining properties of the determinant. In particular, we're going to make use of multilinearity. Okay, and we're going to use multilinearity to sort of split up this first column. We're going to leave the second column alone. Okay, it's going to be BD in each of these matrices. And remember, when you do that, then multilinearity says, okay, well, you can sort of split up the other column then. Okay, so I'm going to write this first column AC, I'm going to write it as A0 plus 0C. Okay, and then multilinearity says, okay, great, it's linear. You can split it up as long as you sort of just are breaking up one column. All right, and now, well, we can compute the determinants of these two matrices on the right more easily. Okay, in particular, like look at this first one here. That matrix is upper triangular, and we learned in the previous lecture video that if your matrix is upper triangular, then its determinant is just the product of those diagonal entries, okay? So we don't even care what's in the strictly upper triangular portion, we just care what's on the diagonal, multiply them together, you get AD. All right, so that's sort of the first piece of the determinant. The second piece, this matrix over here, that one we can get with a similar argument, but it's a little bit trickier because this matrix is not upper triangular, okay? We've got to sort of adjust it a little bit to make it upper triangular. And one easy adjustment that we can make to make it upper triangular is just swap those two rows, right? Apply a swap row operation. And then remember, well, when you apply a swap row operation, what happens is the determinant gets multiplied by -1. This was also a theorem from the previous lecture video. If I swap these two rows, then I get this matrix over here, but you have to introduce a minus sign. Okay, that's what swaps do to the determinants. But now, this matrix over here on the right, it's upper triangular, so its determinant is just the product of the diagonal entries. It's B times C. So this matrix has determinant negative B times C. Okay, and then you just add these two quantities up. This matrix has determinant AD, this matrix has determinant minus BC. You add them up and you get exactly the formula that we said we would get. You get AD minus BC. That's an explicit formula for the determinants of any 2x2 matrix. Okay, and sort of the way to remember this theorem is it's saying that for a 2x2 matrix, the determinant is sort of the forward diagonal minus the backward diagonal. Okay, so now we've seen two different methods of computing determinants for 2x2 matrices at least. So let's go through an example. Let's compute the determinants of this matrix in both different ways that we've now seen. So method one, the method that we learned in the previous lecture video, was you row reduce it, keeping track of the row operations along the way into row echelon form and multiply the diagonal stuff together. Okay, so method one was, hey, you do row operations to get in row echelon form. Now look at this diagonal, 1 and -2 are my diagonal entries, multiply them together. And the addition row operation did not change the determinant. So 1 times -2 is also the determinant of the original matrix. All right, so the determinant is -2 at the end of the day. All right, so that's method one. That's what we learned in the previous video. Method two, this is what we learned in this video just now. The determinant is AD minus BC, so forward diagonal minus backward diagonal. So it's 1 times 4 minus 2 times 3. So it's 4 minus 6, which is -2. Of course, we get the same answer. Otherwise, it wouldn't be a theorem, right? Okay, so you can compute the determinant whichever way you like, whichever one you're more comfortable with. For 2x2 matrices, honestly, the explicit formula is probably the easier way to go. All right, well, great. So that's another way of dealing with 2x2 matrices. What if we ramp up a little bit? What if we go on to 3x3 matrices? Is there an explicit formula for the determinants in that case? And it turns out, yes, there is. Okay, so another theorem time. All right, the determinant of a 3x3 matrix, Well, it's starting to look a little bit uglier now, okay? But what you get is determinant of this big ugly chunk. It's the sum and difference of these 6 terms this time, okay? For 2 by 2 matrix, we just had 2 terms. It was AD minus BC. Here we've got 6 terms. Here's 1, 2, 3, 4, 5, 6. Okay, you're adding 3 terms, subtracting 3 more. And each one of them, like, there's lots of symmetry here. Each one of these terms that you're adding and subtracting, it's a product of 3 entries in this matrix. And if you look even more closely, you'll notice that for each of these terms, you're getting exactly 1 entry from each row and column of the matrix, like AEI, that's the forward diagonal. BFG, that's this entry, and the G down here, and so on. You're always taking exactly 1 entry from each row and column. All right, but we'll talk more about that in a little bit. For now, let's prove this theorem. Let's see where this comes from. And I mean, the method of proof is going to be the exact same as what we just went through for 2 by 2 matrices. Okay, we're just going to sort of use multilinearity to split up the columns to make the matrices upper triangular, and then we can compute the determinants easily. Okay, so it's just going to be a little bit more involved this time because we're going to have to use multilinearity multiple times. All right, so my first time using multilinearity, I'm going to use multilinearity on the first column here. So I'm going to split up this column ADG. I'm going to write it as A00, 0D0 plus 00G. So I'm going to add up those 3 vectors. And again, remember multilinearity, you leave all columns except for 1 alone. So I'm going to leave the second and third column alone. They're the same in all 3 matrices here. But if I add up these first columns, then I get the first column over here. So multilinearity tells me that this matrix is the sum of this determinant is the sum of these 3 determinants over here. All right, great. But none of those matrices are upper triangular yet, right? So I can't compute the determinants right away. This one, not upper triangular, not upper triangular, not upper triangular. So we're going to use multilinearity again. And for example, I mean, I'm going to focus on this determinant first, sort of the very first one on the right-hand side here. I'm going to use multilinearity on the second column now. In particular, the way I'm going to split up that second column is I'm going to keep its first 2 entries there, and then zero them out in the next vector. And like I'm going to split it up so that the first 2 entries are together and the third entry is off on its own. Okay, and again, like what I've done here is I've left the first and third columns alone. They're the same in all 3 of these matrices. Okay, so I'm using multilinearity on the second column here because BE0 plus 00H equals BEH. All right, and the point is now this guy's upper triangular, right? Okay, so I can use my explicit formula for upper triangular matrices. It tells me that, hey, the determinant of that matrix is just the product of the diagonal, AEI. Okay, since that matrix is upper triangular. The other matrix, the one on the right here, this ugly guy here, it's not quite upper triangular, but if I swap some rows, it becomes upper triangular. Okay, so what happens here is if I just swap the bottom 2 rows here, then, well, okay, now it's going to be upper triangular. Be careful when you swap 2 rows, you've got to introduce a minus sign in front of the determinant, right? Swapping multiplies the determinant by -1. But now it's upper triangular, so the determinant of this matrix on the right is just the product of the diagonal. It's AFH, but then with a minus sign still out in front of it. It's minus AFH. All right, so what this does is it tells me that this first determinant over here, well, it equals minus AFH plus AEI, okay? In particular, that gives us 2 of the terms in this explicit formula up here, AEI minus AFH. If you run through a similar argument with the second matrix over here, what you're going to get is the 2 terms involving D in this explicit formula. You'll get the CDH minus BDI from this matrix here. And similarly, this third determinant here, it's going to give you the 2 terms in the determinant involving G. You're going to get the plus BFG minus CEG. So then when you add up all of these terms together, you get these 6 terms, 2 terms from each of these 3 determinants here. All right, so that's the proof. I mean, we didn't run through all the nitty-gritty details, but once you see these 2 pieces here, that's sort of all there is. Everything else is just repetition of that same sort of argument. Okay. Alrighty, and so, I mean, this formula for 3 by 3 matrices, it's a little bit uglier and a little bit harder to remember. Like, certainly I don't remember that exact formula. Like, if you just said, hey, a matrix has entries A, B, C, D, E, F, G, H, I, and asked me to write down what the formula is, I have to think about it a little while and try to work it out. And the way that I work it out is via a mnemonic like this one. What I do is I write down the matrix itself that I want to compute the determinant of, And then I'm going to sort of copy and paste that matrix both on the left and on the right of that matrix itself. Okay, so I'm sort of copying down the entries so that they sort of loop around. Okay, and then what you do, the way that you compute the determinants of this matrix, the way you remember what that formula up there said, was you could sort of construct forward diagonals and backward diagonals. What I'm going to do is I'm going to construct 3 forward diagonals starting from the top entries in my matrix. Okay, so there they are. And I'm going to construct 3 backward diagonals starting from those same three entries. And there they are in red. Okay, and now what the formula says is the determinants of a matrix, it's, well, you multiply it along the diagonals and you add the forward ones and you subtract the backward ones. Okay, so the formula was exactly, it's AEI, well, that's this forward diagonal here, plus BFG plus CDH. Okay, and then you subtract along the backward diagonals, minus AFH, minus BDI, minus CEG. That's exactly the formula that we wrote up above in the theorem box. Okay, so that's how you remember what the formula is. Okay, use a mnemonic like that. It's sort of this product of diagonals thing, very similar to what it was for 2x2 matrices. It's just there's a lot more diagonals now. Instead of 1 forward and 1 backward diagonal, now you've got 3 forward diagonals and 3 backward ones, and they sort of loop around in a sense. All right, so let's go through an example here. Let's do the determinant of this matrix 1, 1, 1, 1, 2, 4, 1, 3, 9 using this explicit formula now. All right, so just use your explicit formula. Okay, forward diagonals are 1, 2, 9, so I'm multiplying those together. And then 1, 4 loops around to 1. Okay, so 1, 4, 1. And then 1 loops around to 1, 3. Okay, so 1 times 3. Those are my 3 forward diagonals. And now I've got 3 backward diagonals again. So start at each of the top 3 entries. So 1, 4, 3. So remember, they loop around, and you're subtracting these backward diagonals. And then 1, 1 loops around to 9. So 1 times 9. Again, subtracted, it's backward diagonal. And then 1 times 2 times 1, again, subtracted, it's a backward diagonal. And then from here, it's all just arithmetic, right? Multiply those together and then add and subtract. 1 times 2 times 9 is 18. This is 4, this is 3, this is minus 12, minus 9, minus 2. And then you just add and subtract, okay? At the end of the day, you get 2. And this is actually a determinant that we already computed earlier, okay? Back when we knew our earlier method of computing determinants based on row operations, we already found that the determinant of this matrix was 2. So of course, we're gonna find 2 this time as well, okay? Again, otherwise that would not be a theorem, okay? You're gonna get the same answer no matter how you compute these determinants. All right, so that's the explicit formula for 3x3 matrices. Let's ramp up again. We've done 2x2, we've done 3x3. How does this generalize to arbitrary matrices? Like if I want an explicit formula for the determinants of a 4x4 or a 5x5 or a 17x17 matrix, how do I get it? Okay, well, the answer is this theorem here. So suppose you've got some n by n matrix, then what it says is that you can compute the determinant in sort of a recursive way. And I'm kind of inclined not even to read the statement of the theorem here, because this is something that is done so much better via example rather than trying to actually parse all of these symbols here. All right, but let's go through it just a little bit. The way this theorem works is it gives you a whole bunch of different formulas for the determinant of a matrix. It gives you one formula corresponding to each row of the matrix and one formula corresponding to each column of the matrix. Okay, and of course, these all give you the same final answer. These formulas, they're equivalent to each other in a certain sense. Like they always give you the same numerical answer at the end of the day, but which one you use, it's a little bit of personal preference, and also it's a little bit of, you know, what do the entries of the matrix look like? We'll talk about how to sort of cleverly choose which of these formulas will be easiest to use for a particular matrix once we get down to examples. For now, let's just imagine we're focusing on the first row of A, okay? So forget the formula down here. This formula corresponds to columns of A. Let's just focus on trying to understand one of these formulas. Let's focus on understanding the I equals 1 formula. So we're sort of focusing on the first row of A. And what I mean by that, like what I mean by focusing on the first row of A is, in this formula, if we set I equals 1, then these entries here, these are exactly the entries from the first row of A, right? This is A11, A12, all the way up to A1n. Those are the entries in the first row of A. So we're sort of taking the first row of A and dot producting it with these weird numbers C, C11, C12, up to C1n. So we just need to figure out what those numbers are, like what numbers are going into this dot product here, other than the first row of A. And they're defined up here, okay? And this is what sort of makes the theorem a bit of a beast, okay? It takes a while to get your head around what these numbers are. These numbers, theseCij's, these are called the cofactors of the matrix. And the way they're defined is, well, they've got a weird sign out in front of them, okay? So it's always you're multiplying by -1 or +1, depending on I and j. Okay, don't worry about the exact sign pattern. We'll talk about that more later. But then it's either +1 or -1, and then times some other determinant. And the point of this other determinant is like, okay, so it makes you a little worried at first. You're using determinants to compute determinants, but this determinant over here, it's a smaller matrix, okay? This Aij with a bar over top of it, it's the matrix that you get if you remove the ith row and jth column from A. Okay, so this quantity here, to compute it, like let's suppose you've got a 5 by 5 matrix, then these cofactors, the way you compute them is, well, they're going to be computed via determinants of 4 by 4 matrices. And then 4 by 4 determinants, you can compute them via 3 by 3 determinants. And once you get down to 3 by 3 or smaller, you've got the explicit formulas that we already talked about. All right, that is way too much of a mouthful. Let's, make just a couple of random side remarks about this theorem, okay, and sort of generally the purpose of it, okay? And then we'll go through some examples, and hopefully when the examples happen, then it'll start to click a little bit, okay? So first off, this theorem, it really is a generalization of the previous two theorems, the theorems for 2 by 2 and 3 by 3 matrices, okay? If you apply this theorem to 2 by 2 or 3 by 3 matrices, you get exactly the formulas for 2 by 2 or 3 by 3 matrices that we talked about earlier, okay? But this theorem also can be used to get explicit formulas for larger matrices, and we'll talk about that in a moment, okay? And yeah, this theorem, it's called a cofactor expansion because these numbers Cij, those are called the ij cofactor of A, okay? And yeah, like I already said, this theorem, it gives multiple formulas for the determinant of A. So you can compute the determinant in multiple different ways. You can do what we call an expansion along any row or any column of the matrix, a cofactor expansion along any row or any column. All right, so that's enough of that. Let's do an example here. So let's compute the determinant of this 4 by 4 matrix, okay, using cofactor expansions. All right, so the first thing I'm always going to do when I do a cofactor expansion is I'm going to sort of make a little checkerboard on the matrix up here of plus and minus signs. So I'm thinking of like this top left entry is sort of associated with a plus sign. The next entry is associated with a minus sign, then a plus sign, then a minus sign. And it just continues in sort of a checkerboard fashion, alternating whenever you change a row or column by 1. Okay, and the reason that I'm going to do that is to sort of keep track of the sign in cofactors, right? I'm going to need this term whenever I compute a cofactor, and this plus or minus checkerboard pattern does that for me. It tells me the sign of that ij entry, of that ij cofactor. Okay, so any cofactor associated with the top left entry, like it had that minus 1 to the I plus j, well that's 1 plus 1, so it's minus 1 squared, which is positive 1. Okay, so this just tells me the sign of that minus 1 to the I plus j term. Okay, now, to make cofactor expansions easiest to use, what we're going to want to do is we're going to want to expand across a row or column that has lots of zeros in it. Okay, and we'll see why in this example. So in this example here, this matrix here, I look for a row or column with lots of zeros. And in particular, this third row, well, that has lots of zeros. In fact, it only has one non-zero entry. Okay, and the reason why that's a clever thing to do is now, if we do our cofactor expansion along this third row, what happens in that formula? Well, I'm going to scroll back up to the formula just really quickly to remind you what it is. So it's going to be this formula with I equals 3 plugged in. Okay, so it's going to be the 3,1 entry of A times a cofactor, the 3,2 entry of A times a cofactor, 3,3 entry of A times a cofactor, and 3,4 entry of A times a cofactor. But the point is, the reason that we're expanding along the third row is 3 of those entries of A are just zeros. Okay, so I'm going to get the 3,1 entry of A times the cofactor, so it's going to be 0 times something. I don't even need to compute that cofactor. Okay, yeah, it's going to be 0 times something. The 0 overrides it. No matter what it is, I just get a result of 0. 0 times something is 0. Similarly, when I do this entry, okay, it's going to be 0 times a cofactor, 0 times something. I don't even need to compute what that cofactor is. I don't need to compute that something. The next one is 1 times a cofactor. I'll come back and talk about this cofactor in a second. And then the last one is 0 times another cofactor. Okay, so notice that, hey, like I've got like a plus 1 in front of this term, then a minus, then a plus, then a minus. Where those signs are coming from are from this checkerboard pattern. I just look in what row am I using? Oh, I do plus, minus, plus, minus. So that tells me the signs that I use in front of each of these terms. Okay, and then last but not least, where is this determinant, where's this 3 by 3 determinant coming from? Like the 1 is coming from, this entry here, but where's this 3 by 3 determinant coming from? Well, that's coming from, what you do is you erase the row and column containing whatever entry you're focused on. So the 1 came from this 3, 3 entry, so erase the third column and third row of that matrix. And notice if you do that, if you forget entirely about this column and this row, what are you left with? Well, you're left with a 3 by 3 matrix that has that in the top left, 2, 1, 0, minus 2. Has 0, 3 in the top right. Oh yeah. It has minus 1, 3 in the bottom left. And it has 2 in the bottom right. So this is just the 3 by 3 matrix that you get if you forget about that column and that row. Right? And those are all the pieces that go into the cofactor expansion. Okay, so now you just compute all of this junk. 0 times something, 0. 0 times something, 0. 0 times something, 0. And then 1 times this determinant. Well, it's a 3 by 3 determinant. I know how to compute that. I just use my explicit formula for 3 by 3 determinants. 2 times minus 2 times 2, oh, that's minus 8. Next four diagonals, 1 times 3 times minus 1 is minus 3. And then 0 times 3 is 0. So those are my 3 forward diagonals. And then I subtract off my 3 backward diagonals. 2 times 3 is 18, but I'm subtracting it because it's a backward diagonal. 1 times 0 times 2 is 0, and 0 times minus 2 times minus 1 is also 0. And then you just add all those up, and you get minus 29 at the end of the day. So that's the determinants of my original matrix. Okay, I know that was a lot. Let's go through the same calculation, except along a different row or column. Okay, so now let's compute the determinants of the same matrix, but via a different cofactor expansion to make sure that we sort of understand what's going on here. So again, I want to pick a row or column with lots of zeros. So this time I'm going to pick the first column. It has 2 zeros. So that's going to help us do this computation a little bit more easily. Okay, the more zeros there are, the better. The easier the cofactor expansion is to do. Okay, and then what it's going to be is it's going to be plus 2 times the cofactor for that entry, minus 0 times something, plus 0 times something, and then minus 1 times the cofactor. Okay, so let's throw all that in there. Okay, so I apologize, we can't really get all of this on the screen at the same time, but so determinants of A, it's going to be 2 times the cofactor, and then the checkerboard pattern plus or minus thing happens. So it's going to be minus, plus, minus. The 0 terms, yeah, they multiply something, but I don't care what they multiply, okay? Because the 0 wins out, okay? You don't need to compute the cofactors whenever you've got a 0. That's why you expand along a row or column with lots of zeros. And then the last one, it's going to be minus 1 times the cofactor. And what is the cofactor? Well, you erase the corresponding row and column. So for the cofactor corresponding to this bottom entry here, erase the first column and bottom row, and you're left just with this 3 by 3 matrix that you compute the determinants of. Okay, so that's where this 3 by 3 matrix is coming from. It's just the top right block of the original 4 by 4 matrix. And similarly, where's this determinant coming from? Well, it's just what you get. Like this is coming from like the 2 in the 1, 1 entry of A. So just erase the row and column that contains that 1, 1 entry, and you're left with this 3 by 3 matrix in the bottom right block. That's the thing you compute the determinants of over here. All right, and now it's just computations that you know how to do. I mean, it's kind of long and ugly, but you know how to do this, right? Because these are 3 by 3 matrices. You know how to compute determinants of 3 by 3 matrices. Use explicit formula here, use explicit formula here. All right, so minus 2 times 1 times 2, that's minus 4. Then a whole bunch of diagonals that have at least one 0 in them. 0, that has a 0. And then one backward diagonal that is 3 times 1 times 3, so that's 9, but we're subtracting it because it's a backward diagonal. Okay, and that whole determinant here is multiplied by this 2 out in front. Okay, it's 2 times the entire cofactor. And then minus 0 plus 0, and then careful of your double negative, this is plus 1 times this determinant. And then I throw that entire determinant in there. Again, it's got 6 terms because it's a 3 by 3 determinant. Okay, but the only one that's non-zero is one of the backward diagonals, 1 times 3 times 1, but it's backwards, so it gets a minus 3 in front, a minus sign in front of it, so it's minus 3. And then you expand all this junk out, and you're going to find that, okay, first bracket is minus 26, second bracket is minus 3. You add them up, you get minus 29, which, of course, it's the same thing we already computed up above. Okay, so you get the same answer no matter where you do your expansion. We could have expanded along any row or any column. Doesn't matter. You're always going to get minus 29, but sometimes the computation is easier to do than other times, right? In the previous, like back when we did our first expansion, we only had to compute one 3 by 3 determinant. Whereas down here, we had to compute 2 3 by 3 determinants. If you expand along a row or column that has all non-zero entries, well, I guess there is no row or column like that for this matrix, but if we expand along the bottom row, for example, you're going to have to compute 3 3 by 3 determinants, one for this entry, one for this entry, and one for this entry. There are 3 cofactors that matter because only one of them is zeroed out. Alrighty, well, let's do another example, okay? That's how it works for 4x4 matrices. What if we try to ramp up even farther? What if we try to go to 5x5 matrices? How do we compute the determinant using cofactor expansions? Well, first step is still the same. Write your plus minus pattern on the matrix, okay? So that's what I'm doing here. My checkerboard pattern of plus or minuses, starting with plus in the top left corner, and then just alternating. All right, and that tells you sort of the sign of the cofactor in each spot. Okay, and then pick some row or column with lots of zeros, okay? In this case, how about the second row of that matrix? It only has one non-zero entry, so maybe I'll expand it along that second row. Okay, now I do my cofactor expansion stuff. The way it works is, well, I'm going to get 0 times some cofactor. If it's 0, I don't care what the cofactor is. I don't have to compute it. And then plus 0 times the cofactor, minus 0 times the cofactor. This one also gives me a minus 0 times the cofactor. And then I get a plus 2 times some determinant of a 4x4 matrix, of a slightly smaller matrix. So that's what's happening here. It's going to be 2, and then plus in front of it, and then times determinant of what matrix? Well, the matrix that you get if you remove that row and column. So remove the row that you're working in, and remove the column that you're working in. Okay, and I'm left with a 4x4 matrix that has 0, minus 1, 2 in the top left corner, and 3, 0, 0, 0 on the right, and then this 3x3 block in the bottom left. Okay, so that's the 4x4 matrix that I'm left with if I sort of squeeze out that row and column containing the 2. Okay, great. I've sort of reduced my 5x5 determinant calculation down to a 4x4 determinant calculation. Okay, so what do I do at this point? Well, how do you compute 4x4 determinants? Oh yeah, we do cofactor expansions. Right? So you're just going to sort of iterate down. Cofactor expansions, they don't tell you the determinant right away. They just tell you how to reduce an n by n determinant down to an n minus 1 by n minus 1 determinant. And you have to keep doing it until the determinants are small enough that you actually know how to compute them exactly. Okay, so do another cofactor expansion. And again, you want to pick some row or column that has lots of zeros. I'm going to pick this time the fourth column. I'm going to pick this column over here because it has lots of zeros, only one non-zero entry. Okay, so what do I get? Well, I still have the 2 out in front of it from up here, so I'm just going to copy that down. I've got the 2 out in front of it. Okay, and then what is the determinant of this matrix if I do a cofactor expansion along this rightmost column? Well, be careful of the sign here, right? Remember, I should have drawn a plus-minus pattern on here maybe. Plus, minus, plus, minus. So for this 3 term in the top right corner, I'm starting with a minus sign in front of my cofactor expansion. So it's going to be minus 3 times some determinant, plus 0 times some determinant, minus 0 times some determinant, plus 0 times some determinant. So the 3 zeros don't matter really. The important piece is I get a minus 3 times a 3x3 determinant this time. Again, the cofactor expansion decreases the size by 1. And the way you figure out what 3x3 determinants it is you squeeze out the row and column containing the entry that you're working in. You squeeze out the 3. And I'm just left with this 3x3 matrix down here. All right, and now it's a 3x3 matrix, so I know how to compute its determinant via its explicit formula. It's going to be that expression that has 6 terms. Okay, so what do I get at the end of the day? I get this 2 is still there, and then this minus 3 is still there, and then times the determinant of this 3x3 matrix. And what is that 3x3 determinant? Well, 0, minus 6, and then plus 1 from the forward diagonals. So that's where these 3 terms came from, forward diagonals. And now subtract off backward diagonals. So let's see, minus 2 times minus 3 times 1, that's 6, but I'm subtracting it because it's backwards. And then 1 times minus 1 is minus 1, but I'm subtracting it so it becomes plus 1 because it's backwards. And then a 0. Okay, and then you just add up all this junk and then multiply by 2 and minus 3. And what do you get at the end of the day? You get 2 times minus 3 times minus 10, and altogether that's 60. All right, so that's our final answer. Okay, and that's maybe enough of going through examples. I want to close on just sort of a final note about when to use cofactor expansions versus when to use Gaussian elimination. And I mean, in practice, use Gaussian elimination. Like if you have a numeric matrix in front of you and you want to compute its determinant, use the method based on Gaussian elimination. It's going to be a heck of a lot faster. This method based on cofactor expansions is very useful for theoretical reasons because, for example, you can use it to get an explicit formula for the determinant of a matrix of any size. For example, if you wanted an explicit formula for the determinant of a matrix of size 4x4, what we could do is we could do a cofactor expansion along the first row. And what we're going to get then is A times the determinant of a 3x3 matrix, so A times 6 terms. and then minus b times the determinant of a 3 by 3 matrix. So it's going to be minus b times, again, 6 more terms. And then plus c times 6 more terms, and then minus d times 6 more terms. So altogether, we're going to get 24 terms, right? 6 terms plus 6 more plus 6 more plus 6 more. We're going to get 24 terms in the explicit formula for the determinant of a 4 by 4 matrix. Okay, and that's really useful for theoretical purposes, even though, like, this is the type of formula that no one's actually going to use in practice, right? No one's going to remember that, and no one's actually going to plug into that formula. They're just going to do the method based on Gaussian elimination. It's a lot faster, okay? But it's useful for theoretical purposes. It lets you prove nice properties of the determinant. And next week, it's actually going to be useful for computing something called eigenvalues of a matrix. It's going to be useful to have an explicit formula because we're going to have variables in the matrices that we're working with. And using the method based on Gaussian elimination when you have variables in the matrix is a lot trickier, actually. Okay, so we're going to like that we have explicit formulas because it's going to give us explicit formulas in terms of the variables that are in the matrix entries. Right, so there are situations where cofactor expansions and these explicit formulas are useful, but I mean, if you just have a numeric method and you want to do a numerical computation, use the method based on Gaussian elimination instead. It's faster. All right, so that's enough of that. That's enough about determinants, actually. So I will see you next week when we start talking about eigenvalues and eigenvectors.